of algebraic combinatorics and algebraic geometry to get one out of bed in the morning. And few places do it better than the University of Michigan, and that's where June Huh has just completed his degree. And actually, he will be starting at Princeton and the IAS as a Clay Research Fellow this fall. And we're very pleased to hear June speak on positivity of Chern classes of Schubert cells and varieties.
Okay, thank you for the introduction and for the invitation and for you to come here on time. So today I'm going to talk about positivity of Chern classes of Schubert cells and varieties. And in fact, earlier this week in this conference, we have heard about a part of the story I'm about to tell you in one of the two papers introduced in the first talk. So this is a paper by a group discussing Chern classes of black manifolds. And what was done here is that if you compute the Chern class of a black manifold, or precisely Chern class of a tangent bundle of a black manifold, and if you express it as a linear combination in Schubert basis or Schubert polynomials, then there was some mysterious positivity around it concerning such expression. The coefficient in front of the Schubert polynomials you see in the expression were always positive. So I'm going to continue in that direction and discuss more generally about Chern classes of Schubert cells and varieties. So these are the two main references concerning this talk. The first is a paper by Paolo Allucchi and Leonardo Mioccia on Chern classes of Schubert cells and varieties. And the second is a paper of mine with almost the same title. So this is the paper by Allucchi and Mioccia. And in the introduction, they state that Schubert varieties are among the most studied objects in algebraic geometry. And it may come as a surprise that something is not known about them. So I'm going to tell you what is not known about them. So the goal of this talk, which unfortunately we do not accomplish, is to understand this table. So the table you see in the column in the left side, you see Young diagrams, and you have one homology class or a symmetric polynomial, if you want, associated to each such diagram. And you expand it in the Schur basis or Schur polynomials. And what you see in front of each Young diagrams in the expansion, for example, 1, 3, 4, 3, 8, 8, 6, 5, 1, associated to this row, are always positive. That is the positivity that I want to discuss about. So whatever that symmetric polynomial or the previous table were, the conjecture of Allucchi and Mioccia predicts that the numbers in front of all these boxes or Young diagrams are non-negative. And I'll briefly explain how you can prove such a fact using algebraic geometry. But what is still missing in the picture is that whether we can see that fact by certain combinatorics. Is there a positive combinatorial rule witnessing the fact that such numbers are always non-negative? So that's the first question I would like to ask. And the second question I would like to ask is this. So whatever those numbers are, conjecture of Allucchi and Mioccia was stated and proved for Schubert cells or varieties in Grassmannians. But as you will soon see, those numbers are so canonical and natural so that they can be defined for, in fact, any algebraic variety, but in particular Schubert cells in any generalized black varieties. So you have these homology classes associated to each Schubert cell in any black variety of any type, and you expand with respect to the usual basis in the homology of such a flag variety, and we expect that these numbers are non-negative in all such cases. So when I first heard about this conjecture about non-negativity, in fact the non-negativity of Chern classes of Schubert cells in Grassmannians, since I had basically zero experience of this sort of combinatorics, I thought that either I could prove it in all generality using only very general geometric rules, so to prove that these numbers are non-negative for all homogeneous spaces or Schubert cells in such spaces, or else I could not prove it even for Grassmannians, because I know very little about what is special about Schubert cells in Grassmannians. But it turned out that, to my surprise, I could prove the conjecture for Grassmannians, and also, which was another surprise, was that I could only prove it for Grassmannians. I will soon tell you what was crucial for me in the case of Grassmannians. I do not know either combinatorially or geometrically how to prove the non-negativity in other flag varieties, and for the reasons that I'll show you. So Schubert varieties in Grassmannians are special in many regards, but I'll show you one reason why they are special. But it is hard for me to believe that these numbers are negative in Schubert cells in other flag varieties, because these numbers are so natural and so canonical. And if there is a combinatorial rule witnessing the non-negativity, as in here, such a rule will naturally generalize to other cases also, so to demonstrate the non-negativity in those cases also. So I conjecture that with little or no evidence that the answer is yes for question B. So what are these numbers? So my true goal in this talk is to convince you that these numbers, or the homology classes or the symmetric polynomials you have seen in the first table, is something very, very natural and canonical. So I would like to start discussing about some generalities of Chern classes of algebraic varieties. So if you have a smooth and compact complex algebraic variety, then you can consider its Chern class. Usually this Chern class is considered in cohomology by taking the tangent bundle, which exists because your variety is smooth, and you can take its Chern class, such a thing lives in cohomology. But in this talk, I would prefer to view everything in the point of view of the homology, so I will count with the fundamental class of the whole variety and view it as a homology class. So any smooth and compact complex algebraic variety has a Chern class. And we have seen a quick introduction to such a definition in the first talk. But in fact, such a homology class can be explained, at least in basic cases, in a completely intuitive and geometric way. So, for example, this Chern class defines element in each homology degree. And for example, the zero-dimensional homology class of this Chern class can be realized by this very concrete algebraic variety. So, besides, if you take a sufficiently general algebraic vector field on your variety V, and if you consider the set of points in your variety where your vector field is zero or vanishes, then such a set is an algebraic subvariety, so it has the fundamental class. And if you take that fundamental class, that is the zero-dimensional Chern class of your free. So the miracle here is that this homology class is independent of what vector field V you have chosen. This variety here varies drastically depending on your choice of vector field V, but their homology class remains the same. And in fact, that invariant homology class is the class of a point times a certain constant, in fact an integer, which is the topological Euler characteristic of V. So this formula here already tells you a bit about what kind of information that this Chern class contains. For example, if you know a priori by different methods that your variety V has negative Euler characteristic, then this equality can be never satisfied, because what you see here is an only set of points, and such a homology class of such a subvariety, zero-dimensional subvariety, should be always positive number times a point. So if you know that the Euler characteristic of V is negative, then you automatically know that you can never find a vector field which is general in this sense. So positivity of Chern classes have something to do with the existence of algebraic vector fields on the variety under consideration. And this simple description of zero-dimensional Chern classes nicely extends to in general. So if you have I general vector fields on V, and if you consider the subvariety consisting of points where all these I vectors are linearly dependent, and if you take its fundamental class, then that homology class remains invariant under your choice of general vector fields, and that homology class is I minus 1 dimensional Chern class. You could take this as a definition of Chern classes, provided that there are many, many vector fields on your variety V. But as we have seen, even in the case when your variety V or X does not have enough tangent vector fields, you can define these Chern classes so as to satisfy various nice properties with respect to short exact sequences of vector bundles, etc. But what I want to point out today is that even if you drop the assumption that your variety is smooth and compact, you could still define the Chern class in a natural way and in a unique such way. So this is the work of McPherson and Schubert. And this is the sense that I'm talking about the Chern class of a Schubert cell or varieties. So the former Schubert cell is non-compact, so there is no Chern class in the usual sense. And the latter Schubert varieties are often cases singular, so there are no tangent vector bundle. But there is a unique natural way of making sense of such an expression. So before going into detail, let's try a toy version of this Chern classes in this general sense. So I can introduce this Chern class as some version of counting, but some very strange or functorial or Grothendieck way of counting. So the point is that we can count in a relative and functorial way, so that the usual counting, I suppose the subject of combinatorics, is the relative counting over a point. So let's consider a finite set S, and I'm going to associate an abelian group that I write by CS, and C is for constructible, consisting of all functions from S to the integer Z. So this group can be viewed in many ways, but I want to view it this way. This is the group generated by functions or constructible functions of the form 1W, where W is a subset of S. So 1W is a function that is 1 on W and 0 outside of W. Let's make this C into a functor. So if I have a map between two finite sets from S1 to S2, then there is a homomorphism between groups CS1 to CS2. So note that the direction of the arrow is preserved. So I'm not pulling back functions. I'm pushing forward functions. So how do I push forward functions? In this way. So by the generation I have remarked earlier, it's enough to define push forward for functions of the form 1W, where W is a subset. And I'm going to push forward this function 1W into this function, What is this function? The value of the push-forwarded function at a point x in S2 is the number or the cardinality of the fiber over x intersected with my set W. Well, this looks strange at first, but in fact this is very, very, very natural. So in particular, if S2, the target finite set, is a singleton set, a point, then this function 1W simply push forward to the constant function on the point whose value is the cardinality of my set W. You have to do something, a little bit of something, to show that in fact the C is a functor. And mostly that's another way of expressing the inclusion-exclusion principle. So if you have two subsets of a finite set, W1 and W2, and if you consider the commutative diagram, which looks like this, which consists of disjoint union of W1 and W2, and the union of the universal set, that is W1 union W2, which both map to point. And if you apply this C and consider the diagram on the right side, then the claim that this is a functor and this every diagram commutes translates to the usual inclusion-exclusion principle. So for example, if you consider the constant function 1 on the top left side, and if you push forward through the point, then as we have seen in the previous slide, it pushed forward to the constant function whose value is the cardinality of W1 plus cardinality of W2. But if you push forward to the W1 union W2 first, then it pushed forward to the function which is either 1 or 2, depending on whether your element lies in the intersection of W1 and W2. And if you push forward that function to the point, then the expression received is this. And the two quantities should be the same. Okay, the point is that this same functor can be defined on the category of compact complex varieties. All you have to do is just replace this cardinality symbol by the topological Euler characteristic, because they both satisfy the same sort of inclusion-exclusion principle. So let's do the same. You start with a complex algebraic variety V, and to V you attach this abelian group CV of constructible functions on V. So this function, constructible function, is a function of the form that's linear combination of functions of the form 1W, where W is a closed subvariety of V, and MW are integers. You could think it as a formal linear combination of closed subvarieties of V. And we do the same. So if you have a morphism or algebraic map between two algebraic varieties, V1 to V2, then there is a natural way to push forward these constructible functions. For the push forward, I only need to define the push forward for the functions of the form 1W, where W is a subvariety of V. And I'm going to push forward that function to this function. So the value of this function at a point x in V2 is computed as follows. You look at its fiber over that point x, which is a subvariety of V1, and you intersect that subvariety with your subvariety W, that's another subvariety, and you take the topological Euler characteristic. That's a number, and it defines a function, and this function turns out to be a constructible function again. So again, the inclusion-exclusion principle for this Euler characteristic says that the C is a functor. So why have I told this to you? Because this functor is naturally comparable to another very well-known functor, which is also covariant functor from the category of algebraic varieties to the category of abelian groups. That is the functor of homology. So this functor, which is which we all very well know, associated to V, the abelian group, which is the homology group of V. And how does these two functors, which preserves the direction of the arrow, compares? That was once a conjecture of Grothendieck and Dahleen, and this is supposed to be the true canonical interpretation of the notion of Chern classes. So the Chern classes is a certain kind of counting which makes both of these countings comparable. So the statement is that there is a unique natural transformation that I'm going to write by CSM from this functor of constructible function C to the homology H, such that whenever you have a smooth and compact algebraic variety, and if you consider the constant function 1 on that variety, if you apply the CSM, then you get a homology class. And what's that homology class? It's exactly the Chern class in the usual sense. And the point is that if there is such a natural transformation, then it should be unique. So the naturality or the functoriality and the normalization on the smooth and compact algebraic varieties uniquely determines the theory of Chern classes, which is valid for possibly non-compact or singular varieties. So indeed, this conjecture was resolved by Robert McPherson and Marie Schwartz independently, and they constructed this functor CSM, proving the conjecture. And in fact, I'll not do this carefully right now, but the only surprising part of the resolution of the conjecture is, I would like to again emphasize that existence of such a functor. If you believe that such a functor exists, it is rather easy to convince yourself that this functor should be unique, because every variety can be compactified and you can resolve singularities of such one of them. And if you have a complete understanding of resolution process, then you know how to push forward constructible functions from resolved variety to the variety of interest. And by this normalization, on the case when V is smooth and compact, you essentially know everything about Chern classes that happens upstairs, and you know how to push forward. That's more or less the proof of the uniqueness of such a functor. So this CSM exists, and you can compute it in principle if you have a complete understanding of resolution of singularities and compactification. So I will denote the Chern class of a locally closed subset W of a compact complex variety V by this symbol, CSM of a W, by which I simply mean that I apply this CSM to the constructible function which is 1 on W and 0 outside. That's an element of the homology group. And the main virtue of this more general theory of Chern classes is that, as I said, this whole theory is very compatible with this very basic counting technique, the inclusion-exclusion. Because if you add these two homology classes, Chern classes of W1 and Chern class of W2, then when CSM is a group homomorphism, you can collect them together, and you can rewrite this constructible function by another combination of constructible functions, and you can divide again, and you conclude that Chern class of the sum is again Chern class of the sum, which is the union and the intersection. And this little generalization makes the whole theory very powerful, because what was missing in the classical theory dealing with the smooth and compact cases is that basically you never have this. Because even if you start with smooth and compact W1 and W2, almost always you will see that W1 union W2 is singular or non-compact. So the usual inclusion-exclusion really does not make sense if you stick into the classical setting. So I would like to argue that this more general Chern class often connects geometry with combinatorics, and this connection is very useful in proving purely combinatorial statements. So before going to the Schubert cell and Schubert variety case, I would like to digress on one other case, the other my favorite case, the case of this chromatic polynomial. So as we know, this chromatic polynomial G of a graph is this function that counts the number of proper colorings of my graph using Q colors. So this function turns out to be a polynomial in Q and with integer coefficients, something like this. And as we know, this chromatic polynomial can be inductively computed using this edge deletion contraction algorithm. So you start with a graph, you pick an edge, and you delete that edge, and you form a second graph by contracting along the chosen edge. And you can check that the chromatic polynomials of the three graphs, the original one, the deleted one, and the contracted one, are related by the simple recursion algorithm, and this can be used to compute the chromatic polynomial of any graph. And I'll not convince you that this chromatic polynomial is really a Chern class of a certain algebraic variety. Why is that? Because you can compute it by a version of inclusion-exclusion principle. All you have to do is encode such an algorithm in the algebraic setting. And what's good about such an encoding is that because once you do that, then you can use various tools developed by algebraic geometers to prove unknown statements about this sort of Chern classes. So one example would be that the coefficients of any chromatic polynomial form a sign-alternating unimodal and in fact low concave sequence. And the only proof known about this statement so far goes through the geometry, and no combinatorial proof is known yet. So how do you encode such inclusion-exclusion in such a basic setting? So you go through this hyperplane arrangement. So introduce a variable for each vertex of G, and you consider the arrangement complement, the complement of the graphic arrangement associated to G. So for each edge, there's one hyperplane setting xi equal to xj. So you notice that this variety is not compact. So there is no usual sense of Chern class. But we do now know that there is such a Chern class. And let's see how to compute such a Chern class. So first thing you observe is that if you construct these three graphs, deleted graph and the contracted graph, then the corresponding hyperplane arrangements or complements of such a hyperplane arrangements naturally fits together. So the complement for the deleted graph is the disjoint union of the original complement, and at infinity, in the hyperplane corresponding to the edge you have deleted, it lives a complement of another arrangement, which is the one corresponding to the contracted graph. Well, once you know that such equality holds, then since the CSM is a functor or group homomorphism, you could decompose this constructible function, which is one on the complement of G prime, as a sum of two constructible functions, and you split it into two, and basically that's it. So, all this computation takes place inside this small H group, which you can identify with the truncated polynomial ring in one variable by identifying Q with the hyperplane class in Pn. And this recursion is in fact the same recursion you have seen in the previous slide for the chromatic polynomial. And all you have to do now is to compute the base case of the induction, and if that works out, and that works out, you conclude that this Chern class of this arrangement complement is more or less the chromatic polynomial. And for example, the proof of this unimodality, the remaining part of the proof is geometry. You have identified a certain invariant with a Chern class, and you want to show that this Chern class is positive or negative, and all you have to do is to show that on this, your algebraic variety, there are many tangent vector fields, or dually, if you want to show that it's negative, all you have to do is that you have to show that there are many differential one forms. So in this case, what you do is that there are many differential one forms on the complement of arrangement with controlled behavior at infinity in whatever compactification you choose. And therefore, you show that the Chern class of this algebraic variety is negative. On the contrary, going back to the Schubert cell case, what conjecture predicts is geometrically more or less the following. So, in fact, a similar argument works for Chern class of a Schubert cell in a Grassmannian. And what you do in this case is that the Schubert cell has many vector fields, which has controlled behavior at infinity, and hence the Chern class is positive. So, the reason that this negativity in the first part is the reason why coefficient of the chromatic polynomials are sign alternating. So the opposite of positive is rather not negative, is sign alternating. Because dual of the tangent bundle is the bundle of differential forms, and if you take the dual of the Chern class, which is positive, then you get something sign alternating. Okay, so now I would like to really start my talk on this Schubert cells and Grassmannians. So there is a good theory of Chern class, and with such a Chern class, we could consider not only Chern classes of flag varieties, we could also consider Chern classes of Schubert cells and Schubert varieties. So this is mostly a reminder to myself. I really know these Schubert varieties by heart until recently. So okay, so you start with the Grassmannian, you fix a partition, and this partition picks up a flag, and then the flag defines a Schubert variety, parameterizing certain planes, which satisfy incidence conditions with a flag of subspace determined by alpha. And those partitions determines the basis in the homology of the Grassmannian. So whatever homology class I have inside the Grassmannian, I can uniquely express as an integral linear combination of the homology classes of the Schubert variety. And this Schubert variety, as we know, is the closure of the Schubert cell, which is a self-isomorphic to the affine space that I'm going to write by S alpha and dot. And this parameterized planes which strictly satisfy incidence conditions determined by partition alpha. And in particular, if I compute this generalized Chern class, CSM class, of my Schubert cell, whatever it is something uniquely and universally determined by this naturality properties. It is a homology class in the Grassmannian, so I can uniquely express as a linear combination of Schubert classes. So that determines the coefficients that is indexed by two partitions alpha and beta. And our goal is now to understand why all these gamma alpha betas are non-negative. But to be fair, I haven't really told you what the CSM S alpha naught are. I just told you that it is something uniquely determined. But there are fairly explicit formulas known for these gamma alpha betas, or this CSM S alpha map. And those were obtained by Alufi and Yamcha. So maybe for the first time I'm going to really tell you what these CSM classes in this case are, or this gamma alpha beta are. So one of the explicit formula which look like this. So you fix two partitions, alpha and beta, and this gamma alpha beta is an integer which is the coefficient of t1 or t to the alpha times u to the beta, a monomial in two variables t and u, which you see when you expand this rational function in t and u. Does this count as formal power series? Okay, so that's what they are. So it's rather mysterious looking formula, but all these gamma alpha beta are encoded in this single expression in a very neat way. So I no idea what this gamma d or this strange expression is, but I really like to just stare at them. So let's do that. So you're now looking at the collection of all gamma alpha beta simultaneously, and for some reason they are all non-negative. There are other explicit formulas, as explicit as this one, but just as mysterious as this one. So here's another one. So I have intentionally used these small fonts so that you cannot read it. So let me read it for you. So there are formulas for individual coefficients gamma alpha beta, and one of them looks like this. So this gamma alpha beta is this number, which is a sum of determinants. Sum of determinants of certain matrices determined by alpha and beta. There are many such matrices. And all those matrices, the entries of all those matrices are certain binomial coefficients. We all like such matrices, I suppose. And well, that's what gamma alpha beta are. So the sum is over all strictly upper triangular non-negative integral matrices with entries LPQ, where these entries LPQ satisfy certain linear inequalities given by the partition alpha.
How does the beta come in?
Beta is here. And the point is that this expression itself is not non-negative. So I have done the computation using this formula exactly once, and this is the result. So if you do this for the partition 3, 2, 1 and 2, 0, 0, then you're adding up the determinants of these 12 3 by 3 matrices whose entries are certain binomial coefficients, and the result is that 3 plus 2 plus 2 minus 1 plus 2 plus 0 plus 0 plus 2 plus 0 plus 1 plus 0 plus 0. So individual determinants need not be positive. There are often cancellations, and for some other reason, the whole sum turns out to be positive. Only in some very special cases, you have a proof of the positivity or the non-negativity using our knowledge of the determinant with certain binomial coefficient entries.
Sorry, I'm confused. In the previous slide, you said there were triangular matrices, but there is one which is not.
Okay, so the sum is over all triangular matrices L, and these entries of this triangular matrix L appears in the actual matrices in some implicit way.
Oh, okay.
But you cannot see it. conjecture. So this number gamma alpha beta, the sum of certain determinants, or the numbers you see in a certain expression is non-negative. But I'd like to point out that why I am focusing on these gamma alpha betas, which are coming from Chern classes of Schubert cells and not of varieties. In fact, I'd like to argue that the Chern classes of Schubert cells is the fundamental one, rather than Chern class of Schubert varieties or flag varieties themselves as a special case. Because Chern classes of Schubert varieties, for example, the Schubert variety S alpha, is simply the sum of all the Chern classes of Schubert cells that contains it, because of this our naturality property. Because S alpha is a disjoint union of all those Schubert cells indexed by beta, which is contained in the alpha. In particular, if you could prove the positivity for the Chern classes of Schubert cells, then you have automatically proof of the positivity for the Chern class of Schubert variety. In particular, if you sum up the Chern classes of all Schubert cells contained in your flag variety, you get the Chern class of the flag variety, which is smooth and compact, so you know what the Chern class is. And in fact, we have seen a positivity of such a statement in the first lecture. But again, there was some mystery behind this positivity. But perhaps if you look at this basic building blocks, then these are stronger, and sometimes proving something stronger is easier. But we do not know that yet. So geometrically, what I actually produce is the following. So you fix a k less than the dimension of Schubert variety, and what you can show is that there is a k-dimensional subvariety, again indexed by partition alpha, that I write by z alpha of the Schubert variety S alpha, such that the k-dimensional Chern class of the Schubert cell corresponding to the partition alpha is simply the homology class of the subvariety z alpha. And this z alpha is reduced and irreducible. And since we know which homology classes in the Grassmannian or Schubert varieties are effective, this proves the non-negativity conjecture, but the proof is very, very far from being combinatorial at the moment. So I want to now tell you what was so special about Schubert varieties in Grassmannians as opposed to Schubert varieties in other Gmod B or Gmod P's. The property I needed, and the property I could only prove in the Grassmannian case, is the following. So as you might notice, everything I do is something very, very general and has really nothing to do with Grassmannians or flag varieties. Everything is almost at the level of group theory. But the property I need is the following. So if I have some algebraic group, let's say B, so B could be any algebraic group, acts on a variety Y with a dense orbit. And I'll say that this Y admits a B finite log resolution if I can resolve the singularities of this variety Y in an equivariant way, but not just that. So the complement of the open dense B orbit becomes a simple normal crossing divisor, the nicest type of singularities you find in algebraic geometry. And of course, the resolved variety X should be smooth. And the important property for me is the expression here. The X should have finitely many B orbits. So even if you start with a variety Y, say a Schubert variety in a certain variety Y, which is acted by this Borel group B, which has finitely many B orbits, there is absolutely no guarantee that if you resolve it in an equivariant way, then you will find, again, finitely many B orbits. In In fact, you don't in most of the known resolutions. So what you can prove is that in this complete generality, you have some variety with open dense B orbit, whatever B you have. And if your variety happens to have this B finite loop resolution, then you could prove that the Chern class of the open part is effective. You could express it as a non-negative linear combination of homology classes and subvarieties. But what I have asserted here is something slightly stronger. So here I have not only shown that this homology class can be written as a non-negative linear combination of classes of subvarieties, but I have shown that this homology class can be written as a homology class of a single irreducible variety. And these two are really very different notions. For that condition, I need something a little bit stronger that I call a regular resolution. And I said that this variety Y acted by a group B has a regular loop resolution if you could find a B finite loop resolution and certain Lie algebraic conditions. So if you look at the isotropy Lie algebra Ex, then it contains a regular element or a generic element of B for the Lie algebra of B for each point in X. But the crucial part in most cases is that, again, it has finitely many B orbits. So if you have that stronger resolution, then you could show that the Chern class of the open part is homology class of a single irreducible variety, Z. And what you can show is that the Schubert varieties in Grassmannians have this finite resolution. You could resolve the singularities of Schubert varieties in Grassmannian so that in the resolution you see again only finitely many B orbits. You don't have this for resolution of Schubert varieties in more general flag varieties. And the basic intuition is that perhaps if you look at the B fixed point in your Schubert variety, which is often singular, and if you look at the tangent space at that B fixed point, so it is a vector space that is acted by this B again, and that often has infinitely many B orbits, the representation in the tangent space. And in the whatever resolution you're choosing, you will have to blow up at this B fixed point at some step, but once you blow up this B fixed point, then this representation with infinitely many B orbits somehow spread out in the exceptional divisor. And you will have to face with these infinitely many B orbits, which comes from this terrible complicated representation of B in the tangent space example. But that doesn't happen for Grassmannians. But when that does happen, then you could realize the Chern class by a rather explicit variety that I write by Z0 lambda here. And the definition of this variety Z is also universal in the sense it is valid for any group or any variety that is acted by any group. So what you do is you pick a sufficiently general subspace of given dimension of the Lie algebra of your algebraic group, and you look at the set of points whose isotropy Lie algebra intersects the chosen general subspace in a non-trivial way. So the subvariety moves in a family according to the choice of your lambda. But that is what it is. So in particular, you could compute this variety in any given cases, even in principle, and you could compute the Chern class in principle in any given cases. And the result of the computations are different, then you know that your variety cannot be resolved with only finitely many B orbits. So, for example, known resolutions such as the Bott-Samuelson resolution of singularities do not have finitely many B orbits in general. Although they do have finitely many B orbits downstairs, once you resolve it, infinitely many B orbits will show up. And that has, at least in one direction, has something to do with the positivity. And I think that most Schubert varieties and black varieties do not have any B finite resolutions, but I do not know that as a fact. Okay, so I'm going to wrap up this talk by posing some problems that I think is worthwhile investigating. Roughly in the order of difficulty. So one thing that we could try to do is first to find explicit formulas or some other better formulas for these Chern classes of B orbits in other flag varieties, G mod P, generalizing the, for example, the formulas of Olympia and Yalcha. So other than the functorialities that I have mentioned for these generalized Chern classes, I sincerely believe that there are many more beautiful properties to be witnessed about these Chern classes, or symmetric polynomials in the Grassmannian case, and I would wish to know more explicitly and better about what those are. And of course, we would like to see a combinatorial proof of the non-negativity conjecture, already in the Grassmannian case, but better in the general case of G mod P. And thirdly, I think it is worthwhile investigating which Schubert varieties in G mod P has, in fact, B finite resolution, the resolution of singularities with finite and many B orbits. In principle, there should be a certain combinatorial characterization of which Schubert varieties have such finiteness condition. And lastly, I would like to understand more about distribution of primes in the homology of G mod P. So what I mean by this is the following. So I have pointed out that homology classes in G mod P, some of them are effective, meaning that can be written as a non-negative linear combination of classes of subvarieties, but some of them are prime, meaning that they can be written as a homology class of one irreducible subvariety. And in general, they are very different. And understanding primes have been a challenge for many, many varieties other than G mod P. But even in the case of Grassmannians, we have absolutely no idea what primes look like in their homology. So, and as we have seen, this existence of this notion of prime could be, if you have certain control of this homology classes, then you have a nice way to test whether a Schubert variety has this like regular resolution or not. So I'll stop here.
We have time for some questions.
If you go back to the slides where you were counting over a point and then replacing the cardinality function with other characteristic to develop Chern classes, I really like that, first of all. It makes sense. Are there other things you could replace chi with? For example, Poincaré polynomial. So if I change chi there to I think Poincaré polynomial, do you still get a functor? I'm guessing the analog of inclusion-exclusion is Meyer-Torres.
That's right.
Does this make sense?
That makes sense, but it is less functorial. That is
Okay.
what algebraic geometers call virtual Poincaré polynomial,
Okay.
and they exist, but they satisfy weaker functoriality properties. And in a sense, this theory of Chern class is a unique solution to what you want. But mainly because of this complicated way of push-forward definition. But if you forget about this push-forward, you could develop the theory in many different ways, and one of the ways is the theory of virtual Poincaré polynomial. And that actually shows up in the theory of toric varieties in connection with the F-vector questions, etc.
Thanks.
More questions?
What are the special properties of the group B? What other groups could I be using?
It could be any group. I mean, that's one of the points that I tried to make. I know basically zero Schubert calculus and Schubert geometry. So I just learned about these properties of algebraic groups. And I had a superficial understanding of the construction of varieties like G mod P. So I thought either I could prove for everything or for nothing. Turned out that I need very special properties which are true only for Schubert varieties in glass models.
The fact that there exists B finite resolution in your sense, is it related with the existence of small or semi-small resolution?
I do not know, but
Because the Grassmannius, I think the Schubert
that's
varieties
right.
exist.
I do not know.
Why would you want a combinatorial proof? I mean, would it actually help you in some way with things you're doing?
Actually, yeah. I don't know. So it seems like that a lot of people like such kind of questions. I mean, it's something very explicit. So.
Often in Schubert calculus sorts of settings, one might think about the big torus T sitting inside B and try to upgrade statements from like homology or cohomology to some kind of torus equivariant story. Can anything like that, does that question even make sense in this setting? I don't know.
I know that there is a way of making sense of it, but I will not attempt to do it right now. But there are relevant papers concerning that direction. So I could point out if you want later.
If there are no further questions, let's